Well, well, well. 2 video lessons in 2 days. It's unprecedented, it's unheard of, but has to be done because we need to get through the second example here. So, get out your notebooklets. We will go back to the next page that we were about to be on, where we're just doing that. It's a 3-part example. It's got parts A, B, and C inside of it. And I know I say this a lot, but it's a challenging one. It's kind of combining a lot of ideas here. We're combining some kinematics, some dynamics in the sense that we've got things working in X and Y directions, and then we're combining it with our new kind of electric field and potential difference principles. It does actually end up being, for the most part, just a kinematics problem, but there is definitely some new stuff that we've learned as well that we're going to be using. So I noticed that only 5 of you have watched the video from yesterday. So reminder, want to keep up with this stuff. For those of you that are planning on going into university and stuff next year, they're not going to care whether you've fallen behind or not. Unfortunately, I mean, like in high school, we usually help you out with that stuff, but they're going to be just moving right forward. So whatever you're doing now, it's going to be helping you out in the future. So just keep that in mind. But like I always say, just do as much as you can. So if you want to just wait a couple days and then watch them all in one day, totally fine. But you know what? I'm going to say this. In general, I've been extremely impressed with how well you guys have been doing. That last quiz that we did, that last test that we did, everybody submitted it. It was awesome. So maybe there was one missing. But anyways, really, really good. Keep it up. Yeah, let's get to this. This is why my videos end up taking so long, because I got nobody to talk to. I'm just talking to you guys, right? So an electron with a mass of 9.11 times 10 to the negative 31 kilograms enters parallel plates, but not from the top like the last question that we saw. It enters from the left. So with a horizontal velocity of 1.5 times 10 to the 4 meters per second. Let's do a Google Meets on Friday. I feel like it would be nice to just like catch up with some of you if you want to. If you're free Friday around this time, probably around 11 a.m. or noon, or maybe even 1, I'll do a Google Meet for us to be able to chat. And if you're struggling with this stuff, I can help you out. Okay, we'll plan for that. So, anyways, with a horizontal velocity of 1.5 times 10 to the 4 meters per second, as shown below. This is exactly what's going on. Great diagram going on here. Now, what we need to do is we want to calculate the length of time the electron is between the plates. We're going to calculate the displacement in its y direction while it's between the plates. I'll get to that. And then its final velocity. So we have to combine the x and y directions. So we already know what's x component of its velocity, but we know that if this is an electron, it's going to have a negative charge, right? And if it has a negative charge, well, it's going to eventually want to accelerate towards the positive parallel plate, right? So that means that it's going to have some sort of velocity in the y direction. It's going to have some sort of vy. That's what we need to find. Okay, enough of this. Let's get started. We'll jump right into it. So the length of the time that the electron was in between the plates. This looks very similar to our projectiles type problems. Like if I turned this upside down, see how this just looks like something that would be maybe launched off of like the roof of a building and would fall down like this. So if we only have acceleration in the y direction, remember that from our projectiles problems, if we only have acceleration in the y direction, that means that the x velocity is constant. What that means is that the x velocity does not change throughout the entire time. The x velocity is going to be 1.5 times 10 to the 4 meters per second. Now, we have to also calculate, we know how far it goes, do we not? We know it's time. We have to find the time. Where did I get this from? Hold on. I'm having a little bit of a... Oh, there we go. 5 centimeters. Sorry. So the idea here is find the length of time that the electron is between the plates. So my drawing is a little bit off here. I guess what I mean by that is that it would actually make it outside of the plates, but it would just have an acceleration upwards. So it would look more like that. Okay. So you have to find how far or how long it is between those plates. So 5 centimeters, what is that? That's delta dx. And that's going to be 5 centimeters, which is how many meters? 0.05. And all we need to do is find delta t. Remember, t is always the same. T doesn't have an x or a y. T is just the same for both, kind of the connector. So delta, let's use a different color here. Delta t is equal to delta d x over delta vx. That's just me, and I don't need a delta there. And we are off to a great start here. Okay. That is just a rearrangement of v equals d over t, like the first formula we learned, right? So delta dx is 0.05 meters, and vx is 1.5 times 10 to the 4 meters per second. So delta t is going to be equal to, if I plug that in my calculator, I will get 3.3 times 10 to the negative 6 seconds. It happens pretty fast. Happens pretty fast. Okay, there we go. So part A, pretty straightforward, but that's just like our projectile problems. The x component of our projectile problems was generally pretty straightforward because there was no acceleration, right? It's when we have the y direction, when there's acceleration, that things get a little bit trickier. So let's write down, let's use a different color here. Let's write down everything that we know about this question so far in order to be able to find the answer. So just a reminder, for B, we are trying to find delta dy. What is delta dy equal to? So we know the charge. We were told in the question that it was an electron. So the charge is 1.6 times 10 to the negative 19 coulombs, always for an electron and for a proton. The time we calculated was 3.3. You know what? I'm just going to do what I calculated. It was actually 3.33. I'm going to do one of those things where I use a little bit more of my I don't use my sig figs necessarily. I keep a few extra decimal places to keep my answer more accurate throughout. So times 10 to the negative 6. I was given the mass. Mass was 9.11 times 10 to the negative 31 kilograms. And my initial velocity in the y direction is what? Am I moving up or down y here? No, I'm moving straight to the side, right? Straight to the right. So my initial velocity in the y direction is 0 meters per second. Okay. And eventually we're going to want to find down here, we're eventually going to want to find v2y. And then eventually we're just going to want to find v2. That's when we combine the x and the y. Anyways, that's all the stuff that we know and we're looking for. Now, what do I need here? How can I find delta dy? I'm thinking delta dy, I'm going to want to use kinematics to find it. I know its initial velocity. I know the time. And one thing that I do know that I can find is I can find acceleration. A is, I don't know, what is this? This doesn't even really make sense. But just so we know, A is findable. We can find A. And that'll help us. Oh man, did I just lose focus there? Uh-oh, I'm going to have to do a little bit of a, come on, work. Nice. A is findable, so that's good. Here is how we find A. We go back to that same, I'm going to keep talking about that quote unquote master formula. And when I do that, I will notice that I have a scenario in which my electric force is equal to QE. Now, remember, force in this type of scenario is conserved. So F net being equal to MA still holds true. It never doesn't hold true. But now what we have is F net from that. Am I going to be able to find it, or am I just going to make things more confusing here? from this relationship right here, where the delta D's cancel, I have Fe equals Q times E. We've seen that before. That's the electric force is equal to the charge times the electric field. Does that help me? Yes, it does. And it helps me in a really convoluted way. And this is why it's actually this is why this question is so difficult, because now we replace this with QE equals MA, but we're not quite finished yet because we don't know E. But again, I go back and I look at what E is equal to. And E is equal to, if I rearrange this, let's rearrange this. E is equal to, well, the Q's are going to cancel, right? And E is equal to the potential difference divided by the displacement. And this is the displacement in the y direction. This is the plate separation. I know this is tough. This is tricky. And it would be, this is why we're doing this problem together. It's hard to know how to just know all these steps without actually doing questions like this before. So this is one thing that I forgot to write down. We've also been given potential difference. Can't forget that. 1.85 times 10 to the negative 16 volts, and we've been given the plate separation, the total delta D, which in this case is again 0.05. So I'm going to call it delta D. Let's call it delta dP. And that just means the total plate separation, just so I'm not getting confused with what the actual displacement of my electron is. Delta dP is equal to 0.05. Okay, now, what am I getting at here? Well, I'm going to replace this E with the delta V over the delta D. And when I do that, I end up with a formula that looks like Q delta V uppercase V, right? We're talking about potential difference, divided by delta D equals MA. Now, the way that this helps us is, I'm going to go, I'm going to run out of room here real quick. I'm going to go right here, and A is going to be equal to all this stuff divided by M. So I'm going to rearrange, but also plug in. So right here now, by rearranging this, I get A equals Q delta V over delta D M. So let's plug in. We know all of those now. Like, that's kind of the goal with these problems, is always just trying to find a way to just work it all around so you have all the information that you need. Now, once we find A, we're going to use kinematics because we're trying to find, this is like a projectiles problem. We're trying to find the displacement in the y direction. We'll know A, we'll know initial velocity, and we know time. That's enough to find delta D. Anyways, A is equal to the charge, which is 1.6 times 10 to the negative 19, multiplied by the potential difference, which is 1.85 times 10 to the negative 16, divided by delta D, which is 0.05, multiplied by mass, which is 9.11 times 10 to the negative 31. And there, just like that, not easy, but just like that, we have found acceleration. It is 6.5 times 10 to the negative 4 meters per second squared. So quite the first step here. We're not even at our final answer for part B, but we are set up super, super, super well to be able to finish it. So I'm going to move down here. I'm going to work right here. I am going to use kinematics now. So kinematics formulas tell us that delta dy is going to be equal to v1y delta t plus 1/2 a delta t squared, right? We've seen that before. Super nice right here. What's v1y equal to? 0. So now all we have to worry about is 1/2 a delta t squared. Let's do it. Delta dy is equal to 1/2 a, which I already found, 6.5 times 10 to the negative 4. Delta T, which happens super fast, 3.33 times 10 to the negative 6 squared. And you plug that into your calculators, and I've done it before because I realized my videos were getting way too long when I was also having to plug in my values into my calculator. Let's give it a direction too, because we know it's going to be up. We already did that based on our, that's why it's important to draw diagrams. If I plug that in my calculator, I get 3.5 times 10 to the negative 15 meters up. So common theme for this section is you're working with these really tiny numbers, right? Numbers are tiny. And so it's important to make sure that even with like sig figs and stuff, keep your extra decimal places as you move on, because it will change your head. So, hey, that was pretty crazy. That was a tough question. Now though, now that we know delta dy, and now that you know what, now that we know A, we can do another kinematics formula to find V2y. I know it's been a while since we've had kinematics, but I mean, we have seen these a lot. V2y is equal to V1y plus A delta t. Right? Seen that one before. V1y again, beauty, 0. That helps a lot. So V2y is just equal to A times delta t. It's really straightforward. 6.5 times 10 to the negative 4 times delta t, which is 3.33 times 10 to the negative 6. And I get a final y velocity. So this is actually not our final question. We want to find V2, right? But we know V2y now is 2.16 times 10 to the negative 9 meters per second up. Okay, so how does that help us? Well, it actually is super helpful because, let me take my other color here. We know Vx. We know Vx was 1.5 times 10 to the negative 4, right? Yeah, no, times 10 to the 4. Yeah, times 10 to the 4 is going really fast. And we know that y is going to be really small. I mean, even smaller than that, but it's making a small little triangle. 2.16 times 10 to the negative 9. So now we have something familiar, a right triangle. We have theta, we have V2. You know how to solve these, right? So V2, we're using Pythagorean theorem. So we're doing the square root of a squared plus b squared. So 1.5 times 10 to the 4 squared plus 2.16 times 10 to the negative 9 squared. Boom. Do that. Plug that into your calculator. You should get, it's such a small number that it's basically insignificant. I don't really like that about this question, but this is the way it is. So 1.5 times 10 to the 4 meters per second. And then we have an angle, right? Angle is inverse tangent of the opposite, excuse me, over the adjacent. Again, our angle is just completely almost insignificant. 2.16 times 10 to the negative 9 over 1.5 times 10 to the 4. And you do that, and I'm running out of room here, and you get such a tiny angle. 8.25 times 10 to the negative 12 degrees. So your final answer ends up being V2 is equal to 1.5 times 10 to the 4 meters per second at 8.25 times 10 to the negative 12 degrees up. Boom. There it is. Like I said, I know I say it a lot. That's a tough one. usually tough when you're seeing them for the first time, but that one in particular has got some tricky steps to it. I think the hardest part with that question is knowing where to start part B. That's the toughest, right? It's hard to know where to start part B. All right. Thanks for watching. Make sure to like and subscribe. You'll have tomorrow to work on the practice problems. Email me if you have questions. Talk to you later.